go back here. Okay, so we are live, finally. Sorry about that. As I said, we've covered most of the material, and that's the list of topics. The stuff we haven't covered is because of the lack of a physical lab. So using a multimeter, using a power supply, using a function generator. So the multimeter is basically the thing that measures the voltages and the currents. And one thing you should get out of this is on a multimeter there are three inputs. There are two red inputs, and there's one black input, right? And this red input usually has a V and an omega beside it, and this input usually has an I beside it. Anybody got any idea why? Let me.
I was gonna say, like, doesn't one just measure the difference of voltages between the nodes, and then one is like an open circuit, so it measures the current flow? That's my guess.
Well, right. So you're on the right track, right? I'm not quite sure what you mean by open circuit, but you're right. The one of them, if you want to measure the voltage, then you connect your two probes. And I probably shouldn't have used black, but you connect your two probes between those two terminals. But if you want to measure current, you connect them between those two terminals. Any thoughts on why you would do that? Vishal, any thoughts on why you might use different terminals for a voltage versus a current? No? Okay, let's try John Wirtz. Any thoughts on why you might use a different way of measuring things for current versus a voltage?
I can't remember off the top of my head. I vaguely remember having having heard it before though, which is let's see. Is it a bit of a shot in the dark here? So that they can handle more, maybe on the current one, or so it's not restricted by voltage for the current side of it?
Yeah, you're getting there, right? So that's actually not that's a little way along the path to where we want to get to, right? So the thing with, if you're measuring stuff, right, you don't want the thing you're using to measure whatever it is to impact, in this case, the circuit, right? You want to measure the circuit as it is rather than the circuit with something else connected to it. So if you have let's just draw a circuit, right? If you have a circuit which has, I probably should use the thinner version of that, right? If you have a circuit, right, and maybe it's got a capacitor in it, right, and if you connect up, right, a voltmeter that measures, and this is a voltmeter thing that measures voltage, right, and I'm not going to use black because that won't show up. I might have to use a grey maybe, right? If you connect up a voltmeter, then that's what you're doing, right? You're putting this circuit element across the capacitor if you're measuring VC. Now, we know that a way to represent this thing here is like this, right? Because this multimeter, this meter, is a circuit. And okay, it's not a linear circuit, but just based on what we've done in this class, you can think about replacing that circuit with its Thevenin equivalent, right? Because it is a circuit, and you could have, maybe it's a ZTH, maybe it's not an RTH, so it's a Thevenin impedance rather than a Thevenin resistance. But you can think about it. So now think about what happens, right? If I don't want this circuit to be affected too much by connecting this thing on, what value do I have to place on RTH? Right? What would be what sort of value should RTH have? I don't think I've muted myself. Can everybody hear me?
Yeah, I can hear you.
Okay.
Yeah, that's fine.
Okay. So yeah, Stephen, everybody else seems to be able to hear me. I got Bishop twice. Why did I get Bishop twice? Let's try, well, I know the answer. Spencer. Ooh. Ooh, it looks like I've got two.
Are you asking what the value of the resistor should be?
Yeah. What value should the resistor have? Sorry, I just accidentally killed my bot. Yeah, what value should that RTH have? Mike Fedora, any thoughts?
I am not 100% sure right now.
Okay, so right, we're
So, is RTH part of the multimeter? Is that what
Right.
we're looking at with this?
Right. So the idea is that I'm measuring the voltage across the capacitor, right, with the multimeter, and I know I can replace just about any circuit with its Thevenin equivalent. So I'm replacing the multimeter with the circuit on the right, with this one here. And I'm asking if that's what the meter looks like, and I don't want to affect the rest of the circuit, the blue part of the circuit, much, what sort of value of RTH should I have?
It would have to be very, very high to prevent it from impacting the rest of the circuit.
Right, exactly, right. So you want ideally, right, you'd have RTH as infinity, but we can't do that. So it's in the mega ohm or maybe even the giga ohm range, right? So it's probably normal sorts of numbers for this sort of input impedance is 100 mega ohms, right? So that's for a real device. Okay, so that's the first part. So we're measuring voltage, but now let's think about measuring current. And it's a bit of a shame because I know you will have the problem when you get into a lab, right? Because one of the problems with measuring current is, and you probably haven't noticed it, but I've been using the term, I've been referring to measuring voltage as voltage across, right? Because you connect the meter across the device. And I've been calling measuring the current through the device, right? And the what that means from a measurement viewpoint is to measure voltage, I don't have to change the circuit at all. I just put one probe on one part of the circuit and I put another probe on the other part of the circuit, right? What happens, what I need to do though to measure current is I need to break the circuit and insert my meter, and this time it's an ammeter, into the circuit like that, so that the current, the full current, flows through the ammeter. Now, again, suppose we replace the ammeter with its Thevenin equivalent circuit. And again, I'm going to ask the same question. Given that we want to measure the current and we don't want to have that measurement impact the rest of the circuit much, what value should I place for RTH? Kyle, Breton, any thoughts? No? I already asked Mike, so let's try somebody else. Dylan, you piped up earlier. Have you got any thoughts on what value RTH should be for current measuring?
So would it be like 0?
Yeah.
Because you want the full current to go through?
Right, so if RTH had something other than 0, then you'd get a voltage drop across, here, right? So ideally, you want RTH for this meter to be 0 ohms. And now we've got a problem, right? If we want a meter to measure both voltage across and current through, in the one case we need an infinite impedance, and in the other case we want a 0 impedance. And that's really, really hard to do, right? You can, right, the meter usually has a switch or a push button to select which of these two things you're measuring. But in order to change from high impedance to low impedance, that would be quite expensive to do just by a push of a button. So the way they do it is they just have separate terminals. And the mistake you will make when you try and do this physically is you will try and measure current. Ryan, yeah, we can do that. I haven't quite got past the intro yet, so we can do that. So the easiest way to change from high impedance to low impedance is to this, but the mistake you'll make is you will try and measure. You'll put the meter on measuring current, but your probes will still be in the voltage measuring inputs. Okay. So anyway, that was a bit of an aside. I'm just going through some stuff that you would pick up in the lab if we had the lab. The power supply, there's not too much different about the power supply. There's two things though. One, the power supply has two on buttons. One of them which is just the normal power on, and the other one is tells the thing to output voltage or current, right? And it's nearly always the case that sometime during semester you forget to turn both of them on. The power button's easy because it'll light up, but remembering there's the output button is usually a button that has either a green LED above it or a green backlight on the button itself. So you can tell whether the output is on or not just by looking at the green light, but unless you're used to it, you don't notice it. So that's one thing. The other thing with the power supplies we have in the class, in the lab, is they have what's called a current limit on them. And sometimes that current limit gets set to 0. So you'll turn it on, and without the output voltage on, you can set what the output voltage is, and then you turn the output voltage on, and the voltage you get out of it is 0. And that's because that it's sort of a safety feature, it's actually so that you can try and approximate a constant current source. The power supplies we have are all voltage supplies, but because of that current limit, and if you turn that current limit all the way down, as soon as you turn on the output and connect it up to a circuit, the voltage goes away, because as soon as a little bit of current starts flowing, it'll drop the output. And function generator. Only funny thing about the function generator is it's got the same problem as the power supply, two on buttons. And then the oscilloscope, the main thing with the oscilloscope is that it has two channels, right? And so you get you get two channels with two leads, with two leads each on each channel, right? And the problem that you get with that is the ground is the same, right? But what people will do is, if they've got a circuit that they're measuring again, let's measure the voltage across the resistor and the voltage across the capacitor. One thing they'll do is they'll connect and this is to the CRO, rather the cathode ray oscilloscope it's called, or the oscilloscope, right? Let me just draw a little screen there, right? They'll connect one set of probes up like that, and then they'll connect the other set of probes up like this. Okay, the trouble is both of these grey leads are ground. So by putting that common ground lead on both sides of the capacitor, you make the voltage across the capacitor drop to zero, because both sides of the capacitor are grounded. Anyway, that's. I just thought I should talk about some of those things. Let me just quickly go here and see if I can't quickly show. Right, so there it is over on that screen. Let's move it over here. Right, so here's the multimeter, or one of the types of multimeter we have in the lab. There's the in fact, why don't I do this? Why don't I just put them in here so you've got access to them? So we want that one. We want that one. And we want that one. I don't think I've got a picture of the oscilloscope. Okay, so there's the multimeter, right? And if I zoom in, you can see this input has volts, ohms, diodes, and capacitors, and this input has current, right? And that's what I was explaining about the two different inputs. Here is a function generator. There's the power button, right? That's obviously a power button. But this one here is the output, the channel, and that one has to be on in order for the any voltage to come out. And we use these function generators to generate the sine waves, the AC signals that we've been using in the class. But it can do all sorts of other weird and wonderful things as well. And this is one of the power supplies. Obviously there's the power button where it says power, but this button here, these things around the green button light up when there's actually power coming out of the device, right? So you connect up red, green, red, black, red, black, red, black, red, black. And here you can see, at least for channel 1 and channel 2, you can set the voltage, but there's also a current limit on there as well. And this one here, actually, that's telling me that one's set to a zero limit, which means nothing will come out if you, right? That's what that's saying. The fact that there's a a zero limit. It means that even if you turn it on and you set the voltage to something other than 2.4 volts, it'll fire up and nothing will come out because the current limit will kick in. Okay, let's just go back Zoom wise. Okay, so in the chat there, Ryan has just asked that the lab and the homework be put off until tomorrow. I am okay with that. Let me do that right now before I forget. So, assessment. So which is the lab? It's homework 8. Yeah, sorry, Giovanni, I forgot to respond to you when you said that earlier, but we can do that. I'm getting there. I just want to go through my usual start of the lecture. I've been increased what I'm saying in this start of the lecture, so I haven't quite got there yet. Okay, so homework 8 and lab 9. Let's just do that. Homework 8 is the phasors one, and I'll need to change it on WebWork as well. Right, so the due date, let's make it for tomorrow, and let's close it tomorrow, and then let's go to WebWork. And what was homework 8 again? It's the phasors one. So it's currently set to close today. Let's set it to close tomorrow. That should be good. Okay. That's that. And I need to do the lab. It was lab 9, I think. I'll push that off until tomorrow. Okay. Homework 9, question 1 and question 5. Okay. Let me just see what else I was going to do, and then we can start going through homework. Just a reminder, I think there's still one person who hasn't booked their oral. There is a bonus assignment available. Please get that done. I have to get your grades in by this date, right? So I need you to have taken the final by this date, because then I can give about, well, a little more than 24 hours. I will upload what I think is your result into Blackboard, and then I will transfer that result into Banner. Okay, so please make sure you book your final. How to make a square wave? Yep, I can do that, Mike. So we have 13 people out of 25 done. I have 11 people booked. I think that means I'm missing one person. If you haven't booked, please book midterm 2. I have released the final. So have a look at that. I'm happy to answer generic questions about the things that are on the final, but I think you should be reasonably capable of doing any and all of these questions. Each question has, I think, 4 options, and I'm not going to get you to do all of the options. I'm going to still ask you to do one of the options. Okay? And so there's the first one. It's basically about simple phasors. This one is about phasors and superposition. This one is clearly about transients because it's got switches. Question 4 is about Thevenin equivalent. And this one is about source conversions. Remember, source conversions is using the fact that Thevenin and Norton equivalents can replace each other. And so you can simplify circuits using those source conversions. Okay, I think we've done the due dates. Does anybody have any questions about other assessment items except for the ones due today, which we've already pushed off until tomorrow?
We push them out till tomorrow?
Sorry? Yeah, I pushed that's what I was just doing in the, so if we go to the live assessment calendar, you will see that homework 8 and lab 9 are now due tomorrow at 11:59 p.m. Okay, I only took the screenshot in the slides this morning, and those I only moved those 2 now because Ryan asked that they be moved. Okay. Okay, so I'm not going to go through the whole course. I think it's more important to answer some of these homework questions. So let's start with the homework question 1 in the one due tonight, which is phasors. So let's go to the phasors one and let's have a look at question 1. Okay. So let's have a look at what it says. What I'm going to do is I'm going to take a screenshot of it and put it back here, wherever OneNote got to.
Oh my god.
Are you a god? Which god would that be? Sorry. What do we want? This is homework 9 Q1, or homework 8 Q1. And let's have a look at no, it's not a printout, it's a screenshot, so it's a picture. Where's my screenshots? There's my screenshots. We grab that one. And let me just fire up Matlab so that I have it available if I need it. There it's coming up. And let's just make that a bit bigger. Okay, so we have V, which is 5 cos omega t plus 60 degrees, and I, which is 3 cos omega t minus 25 degrees. Given V of t and I of t, what is the phase angle between the two signals? And then select the phasor diagram that correctly shows the phasors corresponding to V of t and I of t. Right, so let's just have a look at what that means. So the way we translate this is to 5 angle 60, and that would be volts. And the way we translate that into a phasor is 3 angle minus 25 degrees, and in this case it's amps. Okay, so, and remember with our angles, this is the real part, this is the imaginary part, and the positive direction of theta is counterclockwise. Okay, so the red is the, so we want 60 degrees for V, okay, and we want minus 25 degrees. So if that's the positive direction, clockwise is the negative direction, and it's going to be down like that, I think. So that angle there is 25 degrees in the negative direction. So that's my eye. Okay? And the first question though, so for this one, it looks to me like the answer is C, right? That looks most like what I drew. I didn't draw the V and I to scale. I should be shorter. So I think that means that in this case the answer is C. And then the angle between them is, and I'm not sure which way around WebWork is going to have it, but the angle difference is 85 degrees. But let's just go and check what WebWork thinks it is, right? So I think that one is C, and then this one, I think, and I'm going to cheat and show the correct answers, right? So it looks like there was a possibility of going the other way, right? So the available answers, so one way is to say the angle difference between them is this distance, which is 85 degrees. Or the other way to do it is to say that the angle difference between them is this way, and that's 275 degrees. And both answers are correct. So Giovanni, I don't know, I think I misinterpreted your question about one. I thought you were saying question one, but was it another question in the homework that you wanted to go over?
Somebody else had also mentioned question 5,
Okay.
and yeah, problem 2.
Okay, so problem 2, and so let's have a look at problem 2. We can do that. So let's go to the next problem. Okay, so I'm gonna, again, I'll take a screenshot so I can draw on it over in OneNote. And insert a picture. Insert that picture. And let's just move it over there and make it big so we can see it. There we go. Okay, so we have V of S is 8 cos cos 3t plus 25 degrees. And we have an inductive circuit, right? So the first thing you write down is ZL equals J omega L. And here our omega is 3. So it's J3 and 4 henries. That's a huge inductor, but let's just roll with it. So ZL is J12, and don't forget your units. It's ohms. And so the first part is find V as a polar phasor. So a polar phasor is 8 angle 25, but it's asking us for the angle in radians, right? So it's 8 angle, what's that, 25 on 180 times pi. And I'll have to plug that in. And then the other piece is I, right? So we've got I of t equals Vs on Zt, Z total, right? And the total impedance is just R plus ZL, right? So Vs is 8 angle 25 degrees divided by R plus ZL, 6 plus J12. And I can't do that in my head, so let's go over and get Matlab. I think it fired up. There it is. So let's just get so V angle equals 25 on 180 times pi, right? 4363. And the I equals 8 times x times exponential 1j times 25. Well, let's just type V angle. Okay, so there's our voltage, and then we've got to divide it by our impedance, which is 6 plus J12. Okay, and then we can have if we want to get that into polar form, which we do, and we only want the radians version, then there's the there's that. And
Would you be able to write out what you're doing with this math and the exp function? Just because it's, as someone who doesn't use Matlab very often, it's difficult for me to follow like what's happening here.
okay, sure, I can do that. So all I've done so far is I've basically just in Matlab I've taken this 8 angle 25 and I've written 8 e to the I or j 25 on 180 times pi, right? Because that's the way to transfer a polar number, a polar phasor into Matlab, is to do that e to the I or e to the j angle in radians, and that the pi on 180 is just converting the 25 degrees into radians. And then I just did 6 plus J12. And in Matlab, they don't just use J, they use 1J. as the thing that is the square root of -1. They also use 1i, right? Because Matlab is used by both mathematicians and sorry, my daughter's at soccer practice and the other team cancelled because the coach tested positive. That's no good. Okay, sorry. So does that explain enough about what I did in Matlab? So that's what...
Yeah, I realize now it's the exponent thing. Thank you.
Yep, you're welcome. So that's what this is doing, right? So I can... Let me just copy that and paste that down here. And maybe I should change the color of the text so we can read it. There we go. Okay, so that's all that's happening there. So that gets me the current. What else do I need? I need the voltage V across the inductor, right? And the voltage V of t equals, what does V of t equal? Well, it's just a voltage divider, right? So it's going to be ZL on ZL plus R, right, times Vs. And ZL is J12 on J12 plus, was it 6, times 8 angle 25 degrees. Oops. Like that. And let's just see what that is in Matlab. Right, so V equals, and it's sort of the same thing, it's just, well, it's just IZ, right? I times 1J12 times 12. Right, so there's our and we want the angle, not the absolute value twice. And remember, what I'm doing here is the absolute, the ABS function is the absolute value or the magnitude of the imaginary number, and angle is the phase or the angle of the polar of the phasor. Okay, and let's see what that is. Okay, so there's some numbers. Let's go back to web work and see if plugging those things in gets the right answer. So V as a phasor is 7.1554. And I don't know whether it's going to want units, but anyway, let's leave them out and see if it complains. I as a phasor is 0.5963 with a radian angle of 0.6708 minus 0.6708. Yep. And let's just check that they're correct for now. Oh, it did want units. Oh well. That's what I was afraid of. V and A. Okay, so they're all correct. And it looks like, oh, it does say that the phase shift in the, when you write it in here, should be in radians as well. So it's, for the voltage, it's that times cosine 3t plus 0.9. And for the current, it's 0.5963 times cosine, again 3t minus 0.6708. 6708. And let's just check those answers. Okay. Everybody okay with question 2?
I have a quick question.
Yeah, go for it.
It's not exactly related to question 2, but scroll down a little bit. It's for the equation for Vs, and tell me if I'm wrong, but the way you would turn that into a complex number would be, it'd be 8 cosine 25 plus j8 sine 25, right?
That is correct. Right, exactly.
So if you're given, if the equation is given in sine form, would you do the same thing?
No. So if the equation's given in sine form, you've got to do the phase change, right, to bring it back into a cosine form.
So
Right.
you just minus 90 degrees?
Yeah, subtract 90 degrees, exactly.
All right.
Okay?
That's it. Thank you.
You're welcome. Okay, and then I think the other question somebody had on this homework is question 5. Okay, what's question 5 about? So, consider the following expression. I of t equals cosine 150t plus 20 degrees minus 100 cosine 150t minus 90 degrees plus 40 cosine 150t minus 180 degrees, and it's all in amps. Enter the time domain expression for I of t using a single cosine. Units of phase shift should be in radians. What is the frequency of the function in Hertz? What is the period of the function? Okay, so again, let me just take a screenshot and I'll doodle on it over here. Right, so we just see who that is. No, it's nobody I know. And there's problem 5. Okay, problem 5. We've got this. So basically what we've got to do is we've got to do that addition. So it's going to be 60 angle 20, 60. I wish I could write it, it'd be wonderful. Angle 20 degrees minus 100 angle minus 90 degrees plus 40 angle minus 80 degrees. Okay, so we need to do that summation in Matlab. Well, we can do it on a calculator as well, but I don't want to spend more on a simulator of a calculator than on the calculator, and you can't see my calculator. My webcam isn't great, so it doesn't show the calculator well. Right, so we go, sorry, I've just got a call. I'm going to have to take this. Maybe not. Sorry. Hi Andrew, sorry about this. I'm in the middle of a class. What do you need from me? Sorry, it's Peter Katsoukas. Okay, so let's just go with the draft. That sounds good to me. I have no idea where they're getting $50 from. The only thing I know about, we paid $200 to them. I don't know what the relationship between the 200 and the 50 is. I have no clue. Okay. Yeah, okay, I'll probably do that Monday morning. Okay, great, cool. Thank you very much. Yeah, will do. Bye-bye. I apologise. Sorry about that. So, what we've got to do is we've got to sum those up. So again, we just do the 60 times 1j times 20 on 180 times pi minus 100 times exponential 1j minus 90 times minus 90 on 180 times pi plus 40 times exponential. Oh, and I meant to say something about what somebody said just before. So 1j times minus 80 on 180 times pi. Okay, so this is the answer for Q5. Okay, so there's our answer in complex numbers, but the thing we actually want is the version in polar form, which is probably going to use that more than. Okay, so that's the absolute value, 102. So let's just see if we can get that right first. I'm going to go back here to actually type it in, don't we? So it's 102.9 times cosine 150t plus 0.908. And I'm going to show the correct answers in case I've got it wrong, but I got it right. Okay, they've got a few more decimal places than I put in there. Okay, and then the other question was, what's the frequency in Hertz? Remember, let's just go back and do a couple of things there. So the frequency in Hertz, right? Omega equals 2 pi times the frequency in Hertz. This is the number of cycles per second, and in a sine wave or a cosine wave there are 2 pi radians per cycle. Okay, so in order to get radians per second, you need to do that conversion. So here our omega is 150, so F is equal to omega on 2 pi, which again I can't do in my head, so it's going to be omega equals 150 on 2 on pi, right, which is 23.87. And then the next question is, what is the period? Right, what's the period? So that's saying how many seconds in a cycle, right? F is cycles per second, so 1 on F is seconds per cycle. Okay, so we just need to put 1 on F. So 1 on F is, sorry, I got that wrong. That shouldn't be omega. That should be F. Why didn't somebody call me on that, right? F equals omega divided by 2 pi. Another way to write that is just like that. So we make it a little bit more. So there's our F, and our period is 1 on F. So it's 0.0419. seconds. So let's just plug those numbers in and see what happens. So the frequency in Hertz was that number, and the period was that number. And I've forgotten units, right? So Hz and seconds. Seconds, not Z's. Okay, any other questions for this homework?
Could you show what you typed in the Matlab again
Sure.
to get the combined equation?
Okay, so let's scroll all the way back up. And Jonathan wants to look at question 3. We can do that. Right, so let me just pull all of that and put it over here into
Thank you.
okay, so that's got all the stuff for question 5. And Stephen wants to look at question 3, so let's go look at question 3. Okay, question 3. What do we got? We've got a resistor, an inductor, and a capacitor. And we have a 0 phase voltage with a frequency of 3500 radians per second. And we want to find I as a rectangular phasor this time. So it's the real part and the imaginary part. And find a time domain expression for I, and again the phase shift should be in radians. Okay, we can do that. Again, I'm going to take a picture. And let's just insert the picture down here somewhere. Okay, so what do we got? We want to find IS, right? So IS is equal to VS on the total impedance, and the total impedance is equal to R plus ZL plus ZC. And let's just go, well, we know what R is. ZL equals J omega L. Omega is 3500, so it's J 3500 times 3 by 10 to the minus 3 is a milliamps. And I'll leave a line for that. And again, I can't do it in my head. So ZC is 1 on J omega C, which is 1 on J 3500 C, and C is now 250 microfarads, so it's 250 by 10 to the minus 6, right? Micro is by 10 to the minus 6. And let's fire up Matlab and get let me just save this as what's that, homework 8 Q. So I've got it, and so now our ZL is equal to J 3500 times 3 by 10 to 3 by 10 to the minus 3, which is 10.5, and J10.5, and ZC is 1 on J 3500 times 250 by 10 to the minus 6, and 1.14 minus J 1.14. Okay, so our Z tot, what was R? I've forgotten what R was. R was 8. Right, so our Z tot is 8 plus ZL plus ZC, which is our 8 plus whatever the, because the capacitor imaginary part is negative and the inductor imaginary part is positive, you get a reduction on the inductor, which is inductor imaginary part, which was the bigger of the two. Okay, so it's 8 plus 9.35J, and that is Z tot, but we need IS, so IS is equal to, what was the voltage again? VS 10, and the angle was 0, so it's just 10, and divided by Z tot. Okay, so there's our IS, and it wanted as a rectangular phasor, so let's see if that works as a rectangular phasor. So 0.5279 and 0.6174, and I wonder if we need amps in both or whether it wants amps at all. Let's just check. Oh, I forgot to put the minus sign in for the imaginary part there, sorry. Okay, and then the time domain expression, we just need to convert that into effectively convert it into the polar form. Okay, so it's 0.8123 times cosine 3500 t minus 0.8634. So let's just type that in here. So it's going to be I is 0.8123 times cosine 3500 t minus 0.8634, and it's check answers again, and yeah, they've got a few more decimal places than I'd use, but it's close enough so that it works. Okay, any other questions about today's homework? Okay, I'm going to have to go in about 45 minutes. I need a quick break. Yes, Stephen, let me just take this quick break first. Just a 5-minute break, and then I'll show you what happens. Okay, I'll be right back. Okay. Okay, so Stephen had a question about checking to see day and times that you've made your finals. Now, you have complete control over how your finals work. And what should happen is when you go to book your final time, right? There's the final one there, right? And let me pretend to book, right? You should and I'll use my Gmail account, right? when you book, right, you should get a confirmation email message. And the other thing is, you should bookmark this page. After you've made the booking, you can cancel the booking from this page, or you can reschedule it if you need to. What I've had several students both here and at Fairfield do is not cancel this one or not reschedule this one. So they book several times, and then I'm left hanging because this goes straight into my calendar. Right? You have complete control over my calendar. So you will see, I think, hasn't shown up yet, but you should. Interesting, that hasn't shown up yet. That has now gone straight into my calendar, and if I take that, I think, and go to a new tab, I can now reschedule it, right? So suppose I can't make that booking. Please reschedule. Maybe I need to make it 2 hours later, right? And it update my booking. And again, you'll get an email confirmation. We should see those emails having come in, right? This is what I see, right? I get these two, and you should see some of these, right? So you should see, and you should actually get a calendar entry attached to it. So you should be able to add that to your calendar, and I highly recommend that you add that booking to your calendar so you know when it's going to happen, right? So I see Stephen's just made a booking. Does that? Yeah. So Stephen, I did notice that you've booked the midterm 2 twice, once after the other. Right. So let's go back to my calendar. Right. So. Okay, so on looks like it's today, May 2nd. There are 2 bookings, so either one works. Sorry, you're right, it's tomorrow. Today's May 1st. Okay, so yeah, so you should be able to see whichever booking you have. And then if you need to cancel, please cancel it. Hopefully not. Hopefully you just reschedule. I'm okay with you rescheduling. You don't need to ask my permission to reschedule. If the reschedule option is available, use it. Things happen, right? You get called into work, or you've had an accident, or I don't know, maybe you just decide you need a little bit more time. That is okay. Just reschedule it. I think it'll only let you reschedule within 3 hours, because that's I don't know. I think you once it gets within 3 hours of the time, it won't let you schedule. So it may not let you reschedule if you try and reschedule. So in that case, just cancel it and make a new booking. Okay? So please make use of the reschedule and cancelling things. Okay. I think I'm done with answering questions about, in fact that's most of homework 8, right? So review lab 9. We can review lab 9. Somebody had a question about how to generate a square wave, so let's go do that. Sorry, I'm not quite sure what you're asking, Joel, in the DMs. So let's have a look at lab 9. Wherever the labs got to, let's go to the labs. So here's the lab, maybe, eventually. Now I forgot to change this one. So what we're doing in this lab is a little, and I probably should have given a more of an update. Right? What we're doing in this lab is we're trying to use square waves to simulate transients. And the way we're doing that is we're making the square waves much slower than the transients. Okay? So if you have a look, right, so this, the voltage source we're going to use, and I can't draw on this, let me grab that. And let's make a new lab 9. And insert that. There we go. Make it a bit bigger so we can read it. Right, so what we're doing is we're using a slow square wave to simulate a switch, right? So what we're really trying to do is we're trying to simulate this. Right, which is a switch, and this is I don't know, 10 volts or something. That's what we're trying to do. We're trying to simulate that, but we're doing it with a really slow square wave. So, and that would be like the switch slowly going on, going off, going on, going off. So let's fire up LT Spice and see how to do that. Maybe? Where did it go to? Is it over there? There it is. So let's start a new blank schematic. Let's just save it as save as. This is lab 9. Ooh, it already exists. Let's call it lab 9 new. So again, I like to do the wires first, so let's just do our wires. Right, and then we want to add a component, which will be a voltage source. And then what do we want to do? We want a resistor. Put that there, and then we want a capacitor. Have to put that there. Okay, so there's our circuit. We need a ground, and we need to connect the ground up. and we probably want a spice directive. I don't know, dot tran 01 maybe. And let's have a look at how we set it up. So we go to the Advanced tab, and what we want is probably maybe a pulse. Pulse width, I think pulse might be good. So V initial and V in. Yeah, I think a pulse should do. So V initial, let's make it 0 volts. V on is 10 volts. Time delay. So we want 50 Hertz. So what's that? That's 20 milliseconds. And time on, ooh, for 50, actually let's just give the delay 0. Time on is half of that, 20 milliseconds, so it's 10 milliseconds. And the period is that, and I don't know, 10,000, see if that works. Maybe just 100, maybe 10, maybe 10. Let's try that. I don't know. So let's try that. I don't know whether I've got the right thing happening. I've got to give some values. Okay, so what did I want for my values? I wanted 1.2k and 10 microfarads. So let's go 1200 and what was it? 10 microfarads? 10 microfarads, so 10U. There we go. So now let's have a look at voltage across the capacitor. Okay, so I've only done a certain number of pulses. So that's probably the wrong thing to do. Okay, so maybe I need to change the parameters here. But let's just have a look at the voltage across the resistor as well. Okay, so there's the voltage across the resistor. And let's, for clarity, so there's our voltage. Right, so it starts off at 10 volts effectively, and then it goes, let's just zoom in on the start of it, right, and let's just grab that, and that again, right, and we can okay, so the period should be about 10 milliseconds. Sorry, the period, which is from there to there, should be 20 milliseconds, which it looks like it is. And then the on time should be 10 milliseconds. Looks a little longer, but that's just because the sampling is between there and there. So okay, now one problem with this, it looks like the problem is the I want the voltage across the capacitor to be to have reached its asymptotic value. Okay, so I want the so that means maybe the numbers there are wrong. So let's make those a little longer. So let's go with 0.1 and 0.2. And let's kill that and start it again. And let's just check the voltage across the capacitor. Now it's looking more like it. Okay, so now what you've got is more like what's in the sheet. I apologize for that. I should have checked the numbers. I thought I had, but anyway. Right, so what we're doing in the lab is we're trying to measure the time constant, right? It's either RC or RL on R. And the way we measure the time constant is by looking at how long it takes the voltage to rise by 63.2%, right? And the reason we're doing that is because one time constant is e to the minus tau on tau, so e to the minus 1. So we want the rise, it's going to be 1 minus that. We want to measure that time, because that time will tell us how long one time constant is. Okay, so let's have a look at how we do that. Where's LT Spice gone? There it is. Right, so did I get a... There we go. Oops, I didn't want to do that. For some reason the cursor is not... Does it say click to attach cursor, right click to edit, control click to identify? So click to attach cursor. So we've attached a cursor. Okay, now we can do it. Right, so what we want to do is we want to... Where's it gone? For some reason when I come over here, maybe I just went too quickly. No, it just dropped and then it goes away again. Let's see if we can do this way. Okay, so what I'm doing is I thought I'd be able to use the cursor, but for some reason the cursor is not is stopping where I want to go. So I'm going to do it a bit more granularly, and for some reason it's not letting me put ticks every 5 milliseconds. Only letting me putting ticks every 10 milliseconds. Okay, so what we can do now, let's just make that huge. In fact, yeah, let's make it huge, take a screenshot, and then let's play with it in
You could do 5 milliseconds. You just have to zoom in enough. It
Oh.
depends on how far you're zoomed in.
Oh, is it? Okay, thank you.
Yeah.
Yeah, it'd be nice if it actually told me that. So if I zoom in, okay, so let's just zoom into the piece I'm interested in, and then see, it's taken, automatically set it to, yeah, there we go, that's a bit better. Okay, so and let's just make this big and see if I can get the same. I'll pull that into OneNote as well. Okay, so that's got, so what we want to do, right, is we've got the 1 volt right, this is cutting the 1 volt line at, I would say, T equals 405.5 maybe, or 406 milliseconds, right? And then we want to see how long it takes to go from 1 volt. We're going to go from 1 volt to what's it going to be? It's going to be the maximum value it's going to get to is 10 volts, right? Because that's what the voltage was we put on there. So it's going to go from 10. It's going to go from 1 volt up to 10 volts, and we want to multiply that by, what was it, 60, I've forgotten the number, 63.2%, 0.632. So 63.2%, right, plus 1, because this is the rise from this level. So we need to measure, and let's just figure out what that is in Matlab, right? So 10 minus 1 times 0.632 plus 1. So it's 6.688 volts. Let's get a, right, so it's 6.688 volts. So let's just scroll up and see if we can figure out where it's 6.688. I don't know, maybe it's about there, right? So then we can come down and figure out where that is. So it's about there, maybe, right? So that's at about, I don't know, 418 and a bit, maybe 418 point, I don't know, let's just say 418.5 milliseconds. That's way too many significant figures for this, but that's all right. So then our tau is going to be the time difference, right? It's going to be 418.5 minus 405.5, which is what, 13 milliseconds? And I must admit I didn't calculate what it really should be, so let's go back and calculate what it really should be. Right, so what it really should be is tau equals RC, which is 1200 times 10 to the minus 6, which is probably going to be about 12 milliseconds, I think. Is that right? Does that add up like that? My brain is gone, so let's just fire up Matlab again. 1200 times 10 times 10 to the minus 6. Yeah, so it's 12 milliseconds. So by very rough measurement on the graph here, I got a tau of 13 milliseconds, which for me is close enough to the 12 milliseconds, right? If we were doing this in a physical lab, we wouldn't be able to do it even this accurately. We'd have to do it using the oscilloscope, right, which is what I think the lab has a picture of the oscilloscope, right? We'd be doing it there. It actually might be a little bit better because the oscilloscope has cursors that actually work. So, yeah. Okay. Let's just check what the lab says. Right. Measure the voltage, calculate and measure the RC time constant. We've done that. And then it just asks you to do it again for a different value of C, right? So swap that out for C2 and then do it again and check that it all hangs together. Does that explain enough about Lab 9?
Yeah, that helps. Thank you.
Okay, you're welcome. Oh, okay. Joel's just asking to go over question 4 of the homework. So let's go there. Yeah, sorry, Joel. I'll have to add you to the. Yeah, I don't know how I can do that easily from here. I'll have to add you to the access group to get into the CET236 lines. Okay, so wanted question 4 of the homework. And it's locked me out. Let's try again. So question 4 of phasors. Thinking about it. Looks like it's the one that I have done. There we go. So what's this one about? Okay, so we've got a current source, and we've got a capacitor in one branch, and we've got a resistor and an inductor in the other branch. And the current source is 2 cosine t plus 45 degrees, so omega is 1. We don't really need omega anyway because we've got we're given the impedance ZC and ZL directly rather than their capacitances and inductances. And so we've got to get IC as a phasor and VC as a phasor. Okay, and then select the polar diagram that collect correctly. And what did I select? I selected C. So that's this one down here. So let's see what the problem does. I will put that over here and go back to homework 8. Right, insert the picture. So this one's just a current divider question, really. Okay, so we want the capacitor information, right? So IC is equal to the impedance in the other branch, R plus ZL, on R plus ZL plus ZC times IS. Okay, so that's going to be R, which is, where's my R gone? There it is 4 ohms, plus ZL, which is J4 ohms, divided by 4 plus J4 times plus ZC, which is minus J1, times IS, which is 2 angle 45 degrees. Okay, so that's sort of, that's pretty much all I need to do to get IC. It's just a current divider equation. And where's Matlab gone? There it is. Right, so to do this in Matlab, I need IC equals 4 plus J4 divided by 4 plus J4 minus J1, which is just that, times 2 times exponential 45 divided by, oh, that's what I meant to say before, on 180 times pi. Okay, what I meant to say before is e to the j theta equals cosine theta plus j sine theta. Okay, so that's called Euler's formula, or a variant of Euler's formula, and that's what I meant to say. I forgot to say that when somebody mentioned it, doing the changeover between polar and rectangular before. Okay, so that's the current in rectangular form. What do we need it in? We need it in polar form. So absolute value of IC, angle of IC, and we want the angle in radians, so 4.9628. And it's not what it's got there. Why is it not got what it's got there? What have I done wrong? 2 angle 45? The current in the opposite branch, sorry, the impedance in the opposite branch, so ZL plus ZR divided by the total impedance times 2. ZL plus ZC. Oh, dough.
One J.
Yeah, I forgot to put the 1J in there. Thank you. Okay, that looks a little bit more like it. Right, and then we can do that. And then we get the right answer. Right, so 2.63, and oh, it needs it in it needs the angle in degrees, so we're going to divide by pi and multiply by 180. So 53.13, which is what I had. Okay, and then the voltage across the capacitor is just VC equals ICZC, right? Ohm's law. So we've just got to multiply our 2 angle 45 degrees by minus J1. Sorry, that's not IC. So we need our this thing, 2.263 angle 53 times J1. So it's going to be the same magnitude, but we're going to have to rotate by 90 degrees in the negative direction. That's effectively what this is. So J is equal to e to the j pi on 2, right? So minus j is I think it's going to be e to the minus j pi on 2, right? So we want to subtract, we want to, the phase difference here is pi on 2 or 90 degrees. That's what the VC is. Okay, does that answer the question, Joel? Are you okay with that?
Yeah, thank you.
You're welcome. And Stephen wants questions 1 and 5 on homework 9. What is homework 9? That's the transient. That's lab is transients. So unfortunately, I'm going to have to bail very shortly. But let's have a quick look at homework 9. And I probably want to go here, which is the transients homework, and problem 1. Okay, so here, what have we got? We've got the inductor shown here has 4 amps flowing through it at time t equals 0. Right, write the expression for the current as a function of time for t greater than 0. Okay, so remember the two things we've got to do. I'll see if I can quickly answer this one. I don't know whether I'll get to the other one, but I'll try and quickly answer this one. This is homework 9. Okay, so just with like any transient question, the peer review, it's not worth anything particularly. It is worth a bonus of 5% of the overall course grade. Okay, so you don't have to do it. It's completely optional. I thought it would be good to do as practice. I think it's due, I've forgotten. I think the initial submission is due tomorrow evening, and then the reviews are due a week later or 6 days later. Okay, so this one, sorry, my phone is telling me I need to go. So this one, the two things you need to do are the initial condition, which you've already given, right? And the final condition, which is what happens at infinity, right? At infinity, this circuit looks just like this. Right? At infinity, everything's stopped. There's no changing because this is just a constant voltage source. So the current is, so I equals V on R. I final is V on R. I final, what's R, is 8. So it's going to be 100 on 8 amps. And so that should tell you how to solve for K1 and K2 in the standard, the current equals K1 plus K2 e to the minus T on tau, or in this case, yeah, T on tau. In this case, tau is L on R, the inductance on the resistance. And that should allow you to figure out, so you get so you should then be able to solve for T for the last question. Okay? And then you want to, I'll quickly do question 5, but I really got to go. Write an expression for the capacitor voltage as a function of time. Okay, so in the first instance, and again, let me just take the screenshot. Again, you've got to do initial condition and final condition, right? So the initial condition, I clicked the wrong button. So in the initial condition, the circuit looks like that, right? So it's just a voltage divider, and that'll tell you what the voltage here is, which is going to be the initial VC. And then the final condition, the effective circuit you've got is just that, where this is just R1 in parallel with R2, right? Because when that switch is closed, that shorts out this, so everything, that side is just ignored for the final. So it's just R1 is then connected between here and here. R2 is just connected between the same two nodes, so R1 is in parallel with R2, and you're just interested in how VC discharges, how the capacitor discharges. Does that answer the question, Stephen Owusu? Yeah? Okay, I'm going to bail now, Stephen. I'll send you a screenshot of the check answers page directly, just so you can see what it's telling me. Okay. Sorry, guys, I got to go. Thank you very much for your attention. I will be around later this afternoon for various exams and stuff. Ping me via Discord if you have any other questions. Thank you.